So in this slide, I would like to propose a navigation technique to solving incoherency of seismic reflection. So coherent in the first place means independence of linear connection in the field of parameter, and incoherency simply means when there is non-linear connection in the wave field, which means the wave field is distorted, and the incoherency in the seismic data causes the geological structure in subsurface hard to be delineated. So for this question, given the two figures, and the first figure seems to have a chaotic seismic data beneath the gas cloud, which is an accurate also have an inaccurate depth of the gas cloud, and showing a truncation of amplitude and frequency within the gas cloud, and it also have a incomplete fault structure. So the potential seismic migration technique that I would like to propose in solution to shallow gas is a Q have two, which is a Q computation and elimination factor analysis. So one of the method to improve the incoherency is a Q composition, and Q is a seismic quality factor. The implementation to enhance the seismic data based on the amplitude only, phase only, and amplitude phase. So complete Q composition involves the estimation of Q and then using the resultant Q volume to correct the amplitude and phase effects. So the estimation of Q is developed by wave-based topographic method and perform the analysis on that migrated data, while resultant Q volume can be done in QPDSM and treat the velocity of attenuation medium as a complex number that is function of Q. So the case study in Rio stated that the purpose of the study is to achieve a high resolution image, and one of the three azimuth dataset was initially migrated with a typical TTI PSDM without Q, and the procedure simply used a pre-processing and several iterations of anisotropic velocity update. And as you can see on the right side of this slide, is the amplitude dimming effect resulted from the shallow gas is shown. So this is the figure of the final Q profile and the final velocity model that was then used in the final QPSDM. So these three images are the comparison of the conventional PSDM and the QPSDM result. It can be observed that the amplitude of the event underneath the shallow gas are restored, the wave rate are sharper, and the continuity is improved, and the sag in the structure is reduced. So more importantly, the CIG gathers now are more reliable for the AVO or DHI analysis, and all of this enable the correct interpretation of the stratigraphy within the hydrocarbon zone. So another method to improve the accuracy is elimination factor analysis. Elimination factor analysis enhances the data in terms of velocity model, frequency and amplitude. So it involves two methods, ray tracing method and focal beam method. For the ray tracing method, is based on the number of ray hits on the reflector, and it's also unable to incorporate true amplitude information analysis. So for a focal beam method, it allows us to perform a quick elimination analysis once a velocity model of the subspace has been known. So it gives information on a specific target point, also known as a local method, and also elimination analysis of the surrounding area is relatively unknown. So in order to incorporate both technique into one analysis, an integrated workflow containing both elimination technique is required. So before the analysis begin, a comprehensive velocity model will be built using the field velocity information obtained from the previous seismic data. A wave is sent towards the surface level where source and receiver are placed according to the 3D full acquisition design. So the outgoing wave then converge with the source and receiver, and once the focal beam process finished, the ray tracing analysis was carried out by using the same acquisition setup as in the focal beam. So for multiple source position on the surface, a fan of rays will be shot towards the target depth reflector. However, all the rays will travel through the layers and anomalies and will only reflect back towards the surface once it reaches the depth target and obeys certain rules. So the reflected rays detected back at surface level, and only rays that will be used for ray hit count. So mathematical manipulation to calculate the elimination factor from both methods was used as a basis to new elimination analysis. So the wave extrapolation in focal beam. The wave is a monochrome frequency that contains the information from a single point, creating a local elimination analysis. So it have a continuous simulation that was run to cover the whole reflector, and only special domain analysis is applied to produce a subsurface amplitude analysis, which giving the resolution function. And the uniform amplitude is distributed throughout the layer by the absence of a shallow gas anomaly. So from the figure on the right side is the figure illustrates the focal beam using a wave extrapolation from source at the surface to target reflector in left side, and the receiver at the surface to target reflector on the right side of the slides. So looking into a different aspect of animation, wave interpolation to a complex model may or may not follow with the wave as operation analysis. So for better understanding for our subsurface, multiple wavefronts were interpolate towards reflector, reflected back, and number of rays detected at receiver location were recorded and analyzed. So as shown in figure A, more rays will be reflected if the source was located directly above the anomaly or source placed further away from such anomaly. However, if the source was placed at the edge of the gas anomaly, as demonstrated in figure B, there will be a fewer ray signal that are able to pass through the gas zone and reflected to surface level. So combining all the ray heat map for each location within the reflected depth, a heat count map was produced. So from figure A and B result, it is easier to understand why a comprehensive study of integrated rays and wave analysis is needed. So although the focal beam result indicates a uniform amplitude distribution at reflector 6500 millisecond depth, ray tracing interpolation method indicate only area directly underneath the zone is currently having a greater illumination. So these results are not contradicting but more complementing each other, although it may misleading and difficult for survey design justification. So by combining these two techniques using a mathematical formulation, an illumination analysis was obtained as shown in results figure C. So the usage of scale from 0 to 1 to analyze the illumination of target subsurface reflector can be explained with a single analysis. So the suitability illumination factor analysis to the study area. Hybrid illumination analysis from this work method give a higher confidence levels during a survey design validation before any acquisition took place in this area. So individual analysis might produce a different result in comparison to analysis of the separate outcomes, and it helps the proposing new survey design by focusing to place source and receiver position at the height illuminating zone. So that's all the answer about the migration technique to solving the incoherency of a seismic reflection. Thank you and have a good day.